So we're going to look at deriving the projectile motion equations, and the projectile motion equations are a special case where we kind of assume that there's no air resistance or anything like that, and it's this very special case that we are throwing an object or we're shooting an object into the sky. So we're going to use Cartesian coordinate system here. So the Cartesian coordinate system is your x and your y's. Would be used if I spelled coordinate correctly. Okay, so when we're looking at this, let's actually draw the diagram. So we're going to have the y-axis and the x-axis. And we're going to throw an object. And what we're going to do is we're not going to throw it at the origin. We're not going to throw it just, in specific places. We're just going to choose an arbitrary point and refer to that as x0 and y0. Then we're going to look at how we're throwing it. So we're going to throw it at an angle to the horizontal. So there's the horizontal, it's parallel to your x-axis. You're going to throw it at an angle, the angle of inclination, and you're going to throw it at some speed, some initial speed. So that's going to be v0. So it's the initial speed or the initial magnitude of velocity. We could have also given you the actual initial vector, which then you'll have your x and your y components already. Now, when you throw it in the air and you start throwing it, I'm just going to draw it over here. So there you are, you started to throw it. Your path is in the direction of velocity, but as you're going, gravity is impacting. So it's going to slowly reach a point where it's going to go downwards. It's going to have almost a parabolic shape to it. So one of the other things we need to consider when we're doing all our calculations is that there's going to be gravity involved, and that's the acceleration. So the acceleration vector is going to be minus g, and it's going to be constant minus g in the y direction. So that's going to be acceleration. And now we actually have enough information to go ahead and derive it, because we have looked at our rectilinear cases where we're like, oh, if we have acceleration, we can find velocity through integration. And then we can find position through integration again. So a reminder about that, it comes from our definition. So acceleration is dv dt. And velocity is dr dt. These are vectors now. They're no longer just one dimension. So let's put the vectors in there. So to find velocity, if we are given acceleration, we're going to integrate. And where does that come from? You have acceleration. And again, let's just match it to your one-dimensional system so you remind yourselves. You had this, and you were like, oh, if acceleration is constant, I can just do that. And then integrate. If acceleration was a function of time, I could do the same thing. If acceleration was a function of velocity, I would have to, I can't do it straight away here. Let's show you the steps. So if acceleration was a function of velocity, I would have had dv dt. I would have moved the dt across, and then the dv. The v is in the wrong place. I have to move all the v's to the same sides. Then I have dt, a, v, dv. Then I could integrate. So it's using the same principles that we did with rectilinear motion. And one of the other things we learned was that if we do have a vector, so if A is a vector and it has components, it has the AX component and the AY component, integration is per component. You can integrate by components, so you can break them up. So we can look at just the X case and just the Y case separately. So we'll look at the X component and the Y component. So we're going to have AX and we're going to have a y. Now, if we go back to our diagram, we only had a y component for the acceleration, and we had no x component. So ax is 0, and this is minus g. We also know that ax is equal to dvx dt, and we know that ay is equal to dvy dt. So now we have 0 is equal to dvx dt minus g is equal to dvy dt. And those are both constants, so we can just take the dt across. So we're going to have 0 dt dvx, and on the other side for the y component, dt dvy. And now we can actually look at what we're doing. So we have to just check and confirm that these are separable. So all the t's on one side and all the v's on the other side. And both of them are. So we can then integrate. So we can put the integration signs. Now here we can put in our limits of integration. So if we're looking at our limits of integration, traditionally you start at t0 equal to 0 to make your life easier. And then it's going to go to unknown t, because usually you're solving the equation or you want to substitute in the equation later. So you want to get an equation where you can substitute in t. So you want velocity as a function of time, because you want to solve for like a vt and you want to solve for an rt. So we're going to have 0 for our t0 amounts, and then an unknown t, a t that we're going to eventually fill in at some later stage. Because we don't want them to be the same, we're going to put the apostrophes by integration operators. And then we're going to look at our limits for our velocities. So for our velocities, at t0 equal to 0, we have v0x. And right now, we're not even going to solve for v0x. We're just going to use v0x as the placeholder. And it's going to go to some vx velocity. Same for the y. So now we can just solve our integrations. So 0 can come on the outside, 0t dt prime, v0x vx dvx prime. This is going to be 0, and then it's going to be t prime, 0 to t. This is going to be vx prime, v0x to vx. And we can actually go ahead and put this in as 0, t minus 0. And I'm doing this long way so you can just see every case. Vx minus v0x. So this is going to be just 0. So we have 0 is equal to vx minus v0x. So our vx at any time is going to be equal to v0x. Now let's do the same for the y component side. So we did the x component and the y component. The minus g can come out because it's a constant. 0 to t, dt prime, v0y, vy, dvy prime. Minus g can still stay on the outside. The integral of dt is just t, and it's going to be from 0 to t. This is going to be vy prime, v0y to vy. It's going to have minus g, t minus 0 is equal to vy minus v0y. So that's going to give us minus gt is equal to vy minus v0y. And we're going to make vy the subject of the formula, because remember, we're trying to find an equation that we can solve for any y component of velocity at any time. So we have vyt is equal to v0y minus gt. And now I'm just rearranging my formula. So now I have the x and the y components of velocity. Now at this point, I just want to remind you that this is giving us a velocity vector. So we have a velocity vector at any time is equal to v0x, v0y minus gt, or you can write it in terms of your i's and j's. Your i's and j's are your unit vectors. And let's do that. v0x I hat plus v0y minus gt j hat. And it's this entire thing. So that's just to remind you. And your acceleration was acceleration at t is equal to 0 in minus g. And your acceleration at t in the other format, 0 I hat minus g j hat. So that's just a reminder that you are actually doing everything. It's in vectors, but when you do the integration, you can do it by component. Okay, so now we have the velocity. We can now do the same for the position. So again, we break it up into components, the x component and the y component. So when you break it up into components here, we're going to have the x component. So we're going to have that Vx is equal to drx over dt. But Rx is just the x, so you can also write it like this, dx dt. And we can do the same for our y component. It's going to be Vy is equal to dry dt, which is technically just our y's, dy dt. But I want to again connect it back to the fact we are going to work with vectors. So now we can sub in our velocities in the x component. So that's just v0x is equal to dx dt. We're going to do the same on the y side. So we're going to do this both sides for a point. We're going to have v0y minus gt is equal to dy dt. We're going to try and separate them. v0x is a constant, so when we do this and we have dt, it's perfectly fine. And then we're going to have v0y is a constant minus gt. This whole thing has dt taking place with it. And it is separable, so that was a constant and a t, so that's fine, and all the x's on that side. There is nothing to do with x here, y here, and then all the y's on that side. So now we can actually go ahead and put in our integrations. So we can actually do the integrations. And once again, the limits. So the limits here, remember that when we see dt, we're talking about the limits of t. So the limits of t, we said t starts at 0. So we're going to fill it in on both sides, and it goes to some unknown time t. We want equations where it is a function of t. So we're going to then just make sure that our integration variable is slightly different because we're going to sub in that t. And then we can look at our x, and our x starts at x0. We gave it an arbitrary value there, and it's going to go to some x. Same with our y. It's going to be y0 and y. And now we can just perform our integration. So v0x, we're going to have a t, and then we're going to have, let's do it the long way. So first up, v0x is a constant. So we're going to have v0x equals 0t dt prime. x0x dx prime. We can break this up. So remember, when we do integration like this, we can separate them. So we're going to have, let's do 0t v0y dt prime minus 0t gt prime dt prime is equal to, and let's move our page a bit so we have more space, y0y dy prime. So what we did there is the very first thing we did was we just separated these two, and we could do that, standard integration rules. So we took that one, put it there, took that one, and put it there. Next up, we can take out the constants. So we're just going to do that on this side, taking out the constants. And now we can get on to where we do perform our standard integrations. So let's do our x side first. It's going to be v0x t prime from 0 to t, x prime from x0 to x. And then let's do our y side. We're going to have v0y t prime 0 to t minus g. This is going to be t prime squared divided by 2, 0 to t. And then we're going to have y prime, y0 to y. So we're going to go back to the x side now and just put in our limits. We have v0x t minus 0 is equal to x minus x0. We're going to do our y side, same thing. v0y t minus 0. We're going to take out the half and put it with the g just to make our lives easier. Then we're going to have t squared minus 0 squared. Then we're going to have y minus y0. And now we're just going to rearrange so that the x and the y's are subjects of our formulas, because we want an equation x of t. So we're going to have x is equal to x0 plus v0 xt. Obviously that minus 0 goes away. And then the other side, let's first do an extra step. I'm just cleaning it up a bit before I go ahead and make my y subject of the formula. We have y is equal to y0 plus v0 yt. It's a half gt squared. So what this is actually saying, x is a function of t, where we have x0 plus v0 xt. And y is a function of t, where we have y0 plus v0 yt minus a half gt squared, which means our position vector is a combination of both of them. 0xt, y0 plus v0 yt minus a half gt squared, or written in terms of the i's and j's, 0 plus v0 x t, the whole thing I hat, plus y0 plus v0 yt minus a half gt squared, the whole thing, the j hat. Now keep in mind, we have not subbed in what v0x is and v0y is. We should do that. So we need to go back to our x and y was sitting like that, and we had a v coming out with that angle. So this was v0, the speed. Okay, so we have the speed, or the magnitude of the velocity vector. And then to work out our x and our y components, we take a line down, we make that theta. Let's just, that 90, let's make that theta clearer. I've just moved it further in so you can see what's happening. And we look at, if we want v0x, it is adjacent. So v0x is adjacent to our angle. Hypotenuse is our v0 magnitude, our speed. Adjacent of our hypotenuse is equal to cos theta. So we have v0x is v0, the magnitude of our initial velocity, cos theta. And we can do the same for vy, which we got v0y is v0 sine theta. So now we can sub those into all the equations we created. So you could put it into here, and you could put it into here. I'm just going to zoom out quick. So a reminder of the equations of motion that we just derived. It was, we created the acceleration one through the information we had. We used integration to solve for our velocity. Once we had our velocity, we used integration to get our position vector. And we can sub in our v0s and x's and y's to get the traditional equations of motion coming out.